where we had stopped last time, we had been talking about Ekman transport and then western intensification due to geostrophic circulation. And we hadn't actually talking about yet, running out of words today, the equatorial current and the equatorial countercurrent. Why is there a countercurrent? So we know that the winds that blow, I'll draw the winds in sort of as green arrows. The winds sort of blow this way. And they blow here. Almost centered around the equator. They're actually centered around what we call the meteorological equator, which, due to the difference in land masses, actually shifted slightly north. But we'll worry about that later. Now, if you watch the video that was online that I didn't make, the one about Coriolis Effect, it told you, and I hope you remember, that the Earth is the widest at the equator. So the rotation is felt most strongly at the poles. So the closer you are to the equator, the weaker the apparent turning. So what happens is, and I'm going to redraw these currents in blue on top of this map. So we have currents that begin to travel this way. Oh. Try this again. We have a current here. Hold on. We have a current that travels here and here. And notice I'm greatly oversimplifying them compared to the way they actually flow. And that's why I picked this map. Coriolis effect is actually fairly weak, which is why we get all this meandering up in here. So the Coriolis effect doesn't really make the turn very well, especially in this in the southern hemisphere. It doesn't happen at all. It sort of makes the turn up here a bit and a little bit in here, but things get a little wonky. So what happens? All that water is being blown towards the west, but it doesn't make the turn well, and we actually end up with the same thing we get in a gyre, a pile up of water in this area. And this hill of water has nowhere else to go, so it begins to flow back this way. Well, why does it move in a straight line when the center of our gyres, we know that geostrophic flow begins to get spirally and circular as it flows down the hill? For the same reason it occurs in the first place. There's just not enough Coriolis effect. So it has almost zero effect. We get very little movement of this current. So it doesn't veer in one direction or the other. So the equatorial countercurrent's basically set up because Coriolis effect is weak at the equator. So you get a pile of water at one end, the western end, sort of a sloshing effect, and then it just runs right back down the hill. It's different than geostrophic circulation because it's so close to the equator. There's no real bending of that water as it flows down the hill. So it just flows in the opposite direction of the regular equatorial currents, which is a question on the worksheet. So let's talk about upwelling and downwelling. These are definitions. You've heard them probably 100 times. We've talked about upwelling, downwelling in other classes. But upwelling is the movement of deep water to the surface. And why do we care? Because it's very cold, and cold water can hold a lot of oxygen. It's also very nutrient rich because it's bringing basically marine snow or poop that has floated downward. And this means that areas of upwelling have very high productivity and abundant marine life. Very high, much higher than almost any place else in the open ocean. Downwelling, as it would sound, is the movement of water downward. It takes warm, nutrient-rich water down to the depths, which is what allows life to exist down there. The most important upwelling we talk about here at Mass is coastal upwelling and downwelling. There's a really good animation of this on the links page on the class website. But basically what happens is Ekman transport in coastal upwelling, which is what we get around here. And hold on a second. I'm going to try to put in a blank page. All right, let's see how this works. I'm going to draw the coastline in. I'll make it blue so you can see it. And this is like the typical New Jersey coast. We'll pretend that looks like the beach with the water over here. And when we see coastal upwelling most commonly is in the summer. So we have a wind come in, and it comes in from the south. And that occurs frequently in the summer. It's a hot wind. Southern winds tend to be hot. And it essentially sets up an Ekman spiral. So which way is the Ekman spiral going to move? The overall transport is 90 degrees to the right of the wind. So the water's going to begin to move offshore. But then what happens? It's not like we have no water. The surface waters, and how deep does the Ekman spiral go? About 100 meters down. So basically all the surface water gets blown off. And that surface water had been heated up by the sun and was getting warm, and it's August, we finally get to swim. Cold, nutrient-rich waters well up as this surface water moves out. And that's why when you go to the beach around here, especially in the summer, it can be 90, 95, whatever, very hot on the beach. But the water can be very cold. Just in a day or two of a south wind, the water surface, the water temperature at the coast can go from 70 degrees all the way down to like mid 50s. And this is when we get salps. You guys have probably called them jellyfish eggs, or they're little tiny gelatinous balls, and they are actually a siphonophore. They're a relative of jellyfish, roughly, and they are normally found at very great depths, greater than 200 meters. And when we have that coastal upwelling, that's what brings them on shore, and that's actually why you always find them in August. And they are not fish eggs; they can't hurt you. People are always freaked out by them. Downwelling can happen the same way, though the wind has to be in the other direction. We don't actually get around here a wind coming out of the north. The figures in the book are clearly exhibiting some west coast bias. This would be for the west coast. And the nice animation online, you can actually flip back and forth between the west coast and the east coast. So I advise you to check it out. Other types of upwelling and downwelling. This picture is from the book, and it shows equatorial upwelling. We talked about this very slightly on the other page. There's the true equator, which is 0 degrees latitude, and that's around which the Coriolis force works. And then let me draw it on here. I'll draw that. Hello. Click. That's right here. That's a geographical equator. And Coriolis force is to the right, north of it, and to the left, south. The winds actually don't follow the geographical equator. Those wind belts where we were talking about the trade winds actually follow what we call the meteorological equator, which means this way we would have trade winds blowing. We would also have trade winds that blow that way. And that's what this green arrow is supposed to represent. And this southern trade winds, the trade winds from the southern hemisphere, actually cross the geographical equator. And what that means is they set up a current going, but for a very narrow band, just 5 degrees, north of the geographical equator, south of the meteorological equator, we have an area where one current begins to change direction. So the southern equatorial current bends to the left like it's supposed to. But then in that very small area between the geographical equator and the meteorological equator, the current is still moving in one direction, but now the Coriolis force is bending the more northerly water to the right, since that water is in the northern hemisphere. Well, when you have water moving in two different directions, the water underneath begins to upwell. And that's why we get equatorial upwelling. And the water there is abnormally cool because it's coming from the bottom. And it's an area of, and this is, by the way, almost only found in the Pacific. Weird things happen in the Atlantic. And it provides a lot of the nutrients that the organisms that live in the open ocean need. So equatorial upwelling is kind of an important idea.